Hi folks, in today's video we are going to be learning how to do Hess's Law calculations and an explanation what is Hess's Law. If we have a look at this slide, we have a little definition at the top. So the law of conservation of energy states that energy can neither be created nor destroyed, but it can simply be changed from one another. This law of conservation applies to something called Hess's Law, and Hess's Law states that the enthalpy change for a reaction is independent of the route taken. In other words, no matter what way you go, you're still going to get the same enthalpy change at the end. So let's have a look at example. We'll start with simply A going to B. Now that is, A is, let's say, I don't know, a restaurant, a pub, and B is your house. So you can go home straight there. Or you decide that it's a really good idea that you're hungry, you want to go and get chips before you go home. Perfect, still made it home, you got some chips on the way there, fantastic. You're going home with some friends, you know, there's a few of you in the group. So someone wants to go home via the kebab shop, make that D, because they're really, really hungry and they want a kebab, they don't want chips. And then someone else decides, actually no, I don't want chips either, I want to get a Subway. So then you have to go and get a Subway on the way home before you get home. Do you get home? Yes, you do. You still go from A to B, you just go a slightly longer way. You've got food to help you feel better, so again, you're not using up any more energy. So let's go with delta H, just suggests the enthalpy change for 1. We can do delta H2 and 3, and then 4, 5, and 6. So we can get home into a few different ways. We can just simply get home via delta H1, or we can go home via delta H2 and 3, and then lastly we can go home with, oh that should say 3 there, sorry. We can go home via 4, 5 and 6. Now those two here, they all equal the first, because you're still going home, you're just going home a slightly different way, and you still reach your end goal at the same point. Now a couple of things that are important to remember. Hess's Law can be used to calculate the enthalpy information of 1 mole of a substance, so 1 mole, that's really, really important, from elements in their normal state. If you're looking to calculate this, you basically want to go to page 10 on the data book. There's some information to help you be able to calculate the questions. Usually they're in the question, but if they're not, page 10 is where you want to go, so feel free to have a look at that on the data book just to give you an idea of what the page looks like. So let's have a look at example. Here we have a past paper question, and you can recognise it's Hess's Law by the fact that there's lots of different equations, and it says calculate the enthalpy change in kilojoules per mole for this reaction using the following equation. The following equations. The one at the top is what we call the target equation. That is what you want to get to. So you want to make sure that everything's on the correct side and that you have the correct number of moles of everything to do your question. So let's have a look at the equation. We're going to call this one number 1. So let's have a look. Have we got a carbon in the target equation? No, we don't. We've got some oxygen, perfect, and we've also got carbon dioxide. Now let's have a look. Carbon dioxide is on the right hand side in the target equation. It's also on the right hand side of equation 1. So what that means is we just simply leave equation 1 alone. We don't need to do anything to it. If we have a look at equation 2, we can see that we have no S in our equation. We've got an oxygen and we've also got an SO2. If you have a look at the target equation, we've got 2 SO2s. So what that means is we need to times that equation by 2. And then finally, we're going to look at equation number 3. What you want to do is again have a look at the same. We don't have a carbon, we don't have a sulfur, but we do have this C2S, except it's on the other side of the target equation, so you're going to have to reverse it. Now I'm just going to change colour. If you take the ones that we don't have, so we've got carbons, for example, and we've got sulfurs. Now they're not in the target equation, but they get cancelled out when you reverse them and you times them by 2, so you don't really need to worry about it. We're also in times in equation 2 by 2, so that means we're going to have 3 oxygen in total, so they usually sort themselves out. So what does that mean? Equation number 1 is simply just going to be minus 393.5. 2 is going to be times by 2, which is minus 593.6. And then equation number 3, you reverse it. What that means is just change the sign. So 87.9. And then your total, you just simply add them all up. So be careful with your brackets just because you've got a lot of minuses, just so that you can have them all in the right place. And then once you pop that into your calculator, you're going to get a total of 1,075 kilojoules per mole. And that's Hess's Law. Feel free to try some examples as well, just so that you understand the concept. And if you've got any issues, feel free to let me know.